this is going to be a very special talk because it's for Hanukkah. And since it is a talk about Hanukkah, then we will talk about tori. And we'll talk about tori. So let me just first show you guys all my slides. So here we go. All right. So the topic of the talk today, sorry, I'm just going to change the display. I'm trying a new way of giving a talk here. Okay, so the topic of the talk today is going to be Furstenberg's times 2 times 3 theorem. And in the picture, there is a torus, which is right over here, and all of this. But now you ask, where's the torus here? So if this is going to be the first part of the talk, I'll talk about what's a torus exactly. Sorry, so let's first talk about what's a torus. As some of you may have understood from the brief conversation that we had right before the talk began, I recently came from the Hebrew University. And before I gave this talk, I was talking to some other graduate students about this talk, and I was saying, oh, I'm going to talk about actions on tori. And I was very surprised to learn that at the Technion, or maybe in Haifa in general, a torus is something different from what I thought. So this is the torus at the Technion. It's a very delicious torus for Hanukkah. And I view a torus in a very different way. This is how we view a torus as dynamicists, or maybe in Jerusalem, or I don't know what. So the way that I see a torus is we take a vector space V, and we have a lattice within the vector space. That's going to be a discrete set of complete dimension.
We have we already have a question.
Yes.
As a local, I'd like to point out that we do know this is a full torus.
That this is a what torus?
A full torus, not a torus.
Okay, thank you very much for this.
Even in Haifa, we know.
Thank you very much for this. I, again, am not a topologist. I'm a dynamicist, so I view tori slightly differently. But the way that we see it is that we have a vector space V, and we have a lattice within the vector space that's a discrete set of complete dimensions. So, for example, if these are the X and Y coordinates, and the lattice would just be the points that are like this, for example. These would be lattice points. So a lattice would be something like this up to my terrible drawing skills. And then they go in every direction infinitely. And now the torus, and now since this lattice is a discrete set of complete dimension, then the torus would actually be V mod the lattice. So for example, you could view this part here as being a torus. So this is all good, but let's see some nice examples. So when I think of a torus, the classic example I think of is R mod Z, when this is obviously additive groups, and this is congruent to 0, 1. And then in general, we could take R mod alpha Z, where alpha is a non-zero number. For example, if this is the line, this is Z. For example, this is 0. Then R mod Z would just be, you could take these guys to be a set of representatives for R mod Z. If it was R mod alpha Z, then you could take, for example, this here to be a set of representatives. So this is a very simple example, which we'll deal with today. We can ask, what's a multidimensional version of it? So this would just be Rn mod Zn, which would be the multidimensional version of R mod Z. And then we'd also want a multidimensional version of R mod alpha Z, where we don't take alpha to be 1. So for this, we would do Rn mod X times Zn, where X is the matrix with non-zero determinant. And now these are all over R, which means that this is all over a field of characteristic 0, and we have analogs for fields of positive characteristic for all of those. Today, we'll only see this one, which I'll discuss later. But in short, it's going to be Laurent series with coefficients in a finite field, mod the Laurent polynomials with coefficients in the same finite field. So now that we know what's a torus, we can ask some basic questions. Some questions that I like to ask, or dynamicists in general like to ask about tori, is what are the invariant sets under certain nice automorphisms? So let's start with this following question. Let's take the one-dimensional torus. Which sets are invariant under the times n map? where n is a natural number. That is, which sets of the torus would satisfy that NA mod 1 is going, where A is in A, is just going to be equal to A. So let's give a very simple example of a first set like this. Let's take the set, this finite set, A, which is 0, 1 divided by n minus 1, all of these guys. So I claim that this is going to be, and this is just going to be, if you multiply the set by n, then you'll just get A again. Why? Because if you look at n times k divided by n minus 1, then this is like doing n minus 1 plus 1 times k divided by n minus 1, which now if we take this out, then we'll get k plus k divided by n minus 1, but if we take it mod 1, is now going to be equal to k divided by n minus 1. So that's why this makes sense. Now I'm just going to erase this so that we have room to see the rest of it. So this would be something that would make sense. And now, now this set is very simple. A very easy property of this set is that it's finite. So a question is, can we find any infinite sets that have this property? So turns out that the answer is yes. And I will give an example for n equals 2. And those of you who are very ambitious can generalize this example for any n, which is a natural number. So here's the motivation, and n equals 2. So let's take the one-dimensional torus. We know that every number between 0 and 1 has a binary expansion. In general, every number has a binary expansion, but for numbers between 0 and 1, it has a binary expansion of this form. Now let's look at what happens when I take this number in binary expansion and multiply it by 2. So I'm going to multiply this by 2, and before that, I want to write this number out instead of the sum as a vector, as a binary vector, which corresponds to the sum here. So when I multiply it by 2, all what happens is that I just shift this vector. That's why I wanted to go through the vector. So from here, we get a very nice idea. If we avoid the numbers and instead we look at binary sequences, and then we take the shift map, that's a map that simply takes A1, A2, A3 to A2, A3, A4, and so on and so forth. And then we get that a set A of the torus is going to be times 2 invariant if and only if the set of binary sequences corresponding to these numbers is going to be shift invariant. And this is useful because maybe it's easier for me or for some of you to think about which sets of binary vectors, infinite binary vectors, are invariant under the shift map. So here's an example of such a set. We can take the set of binary vectors which have zeros in all the odd coordinates or zeros in all the even coordinates. So clearly this is shift invariant, because if you shift something that has zeros in the odd coordinates, you get something with zeros in the even, and vice versa. And this would correspond to this set, which is a set of numbers between 0 and 1 that have only even coordinates or only even powers here or only odd powers in their binary expansion. So here we can construct infinite sets that are invariant under the times n map, and at least for n equals 2, and you can try it in general for any n at home. And now we can ask a more difficult question. So can we construct these types of things? Yes, please.
When you say invariant, do you mean because these aren't homeomorphisms, so they're not one-to-one. So do you mean that the image of a set is contained in a set or equal to it?
Equal.
Okay.
So it means equal in this sense. So now that we have this, then we can now ask the question of what if I want a set that's invariant both under times n and times m? Let's start with the baby case. What if I want a set that's invariant both under the times 2 map, which we found a set invariant under the times 2 map, and also invariant under the times 3 map, and it's infinite? Can I construct a set like this that's not going to be the entire torus? So firstly, the answer is yes, in a way. Let's take the set Q. Q mod Z. This is infinite. It's invariant under the times 2 and the times 3, and it's not the entire torus. but it's dense. So we can ask, moreover, can I construct such a set like this that is not dense? And Hillel Furstenberg from the Hebrew University answered this question as with no in 1967. So more accurately, the theorem that he proved is the following. If n and m are two numbers that are not rationally dependent, that is, we cannot raise them by powers to get one another, then the only infinite and closed set of the torus, which is invariant both under the times n map and the times m map, is going to be the torus itself. So, and this is in general from here we get that it's not just something that's invariant under the times n and the times m map. In general, if we take some multiplicative semigroup that's not going to be cyclic, that is, it's not of the form a to the n where n is an n, this, for example, then the conclusion holds. For this type of thing, we saw that this would be, if you take a equals 2, then we already saw a counterexample. So for any type of multiplicative semigroup that is not generated by one element, then we get that the only infinite closed subset is going to be the torus itself. Now, this is a nice theorem, but I would like to state it in a different way and look at a nice consequence of this. So I'd like to state it in the language of orbits. So let's take some alpha, and I'm interested in the orbit of alpha under this semigroup so it would be something of this form. So this would just be, so if this is the semigroup, n to the k times m to the l, where k and l are in n, then the orbit would be all of these guys times alpha. So firstly, notice that this is going to be an invariant set, and therefore its closure is going to be both a closed and invariant set under the times n and the times m map. So if it is infinite, if this closure is infinite, then it must be the entire torus. So this gives us a very nice, classification of orbits of such actions, and that is that every orbit of the times m times n map for such n and m that are not rationally dependent is either going to be finite or dense. So on its own, it's a very cool theorem, in my opinion, because it gives a complete classification of orbits for these types of actions that are not for these types of actions. But now it has nice consequences as well and very nice applications. So before that, we just wanted to say that this property of being finite or dense, we'll call it topological rigidity in a way, because it just shows that every orbit has to be like this or like that. You don't have any other options. And we call this property ID, which stands for infinite implies dense. Technically, it should be called IID, that is invariant infinite implies dense, but IID is from probability theory, so we'll let them keep their own name. So now let's talk about a nice application of this theorem. So this is going to be an application to Diophantine approximation, which is a field of numbers theory, which discusses how well can you approximate irrational numbers with rational numbers and with their denominators. More precisely, if we have a set of denominators, delta, then can we find for every epsilon and every irrational number alpha some n from the set of denominators and some m in z, such that alpha is close to m divided by n up to epsilon divided by n. That is, we can approximate alpha very well with a rational that has a denominator from the set of denominators that we chose. So here, there's a nice theorem, a very old theorem by Hardy-Littlewood, which says that in order for this to hold, this set of denominators must satisfy for every alpha that's irrational, that n alpha mod 1, where n is in the set of denominators, must be dense in the torus. So let me explain in short why these two things are equivalent, because if I would rewrite this by doing a common denominator, I would get alpha n minus m divided by n is less than epsilon divided by n. Now we can cross out these n's, and then this just says that n alpha is close to an integer up to epsilon. That is, for every alpha, this set here is going to be dense. So now let's use this. And why does this somehow remind us of Furstenberg's theorem, because this here, if we take this delta to be a multiplicative semigroup of the form that we like, that this here is exactly an orbit. So by Furstenberg's theorem, if we take, for example, delta to be 2 to the k times 3 to the l, then all orbits are going to be either dense or finite. So in this way, it suffices for me to show that such an orbit is going to be infinite in order to show that it must be dense. So let's take an irrational alpha, and I want to show that its orbit is infinite. In order to do so, I'll show that the orbit contains an infinite subset. And this is going to be the subset. I claim that if I take L equal to 0 here, then just 2 to the k times alpha mod 1 is going to be infinite. And this is very simple, because if it is not, then we can write this as some finite set like this. But then if we put k equals n plus 1, then it will be in here, and therefore it has to be here. So therefore, 2 to the n plus 1 times alpha must be equal to 2 to the j alpha mod 1 for some j which is less than or equal to n. But then if we do some arithmetic, then we can get that alpha times some number which is non-zero, since j is less than n, would be an integer. And in order for this number to be an integer, we would require that alpha would have to be rational, but we chose an irrational alpha. So that's a contradiction. Therefore, this set is irrational, and it's contained in this set if we put alpha here. And therefore, we obtain that the orbit must be infinite. So since this orbit is infinite, it's also times 2 and times 3 invariant clearly as an orbit. So by Furstenberg's theorem, it must be dense. So now we can go back and apply Hardy-Littlewood's theorem and claim that, and say that now we get that for every alpha and for epsilon greater than 0, we can find some n and m basically, and some k and z, such that we can approximate any alpha up to with some rational number, which is of this set. So this is this is basically a cool idea of how we could use this dynamical theorem to find things and to prove things in Diophantine approximation. And now another question that we can ask, we could ask some more questions. Like, firstly, can we generalize this? What does generalize mean? In this case, we talked about the one-dimensional torus, but we earlier discussed that there is multi-dimensional tori as well. So one question is, can we generalize this for a multi-dimensional torus? For example, this torus here. And turns out that the answer is yes. Daniel Behrendt from Ben Gurion University proved such a result, and I'll discuss this shortly. And another question that I'm interested in, since a large part of my PhD research actually relies on this, is can we find some analogs for these tori for fields of positive characteristic? And before we even go into that, what does that even mean? All of this I'll discuss shortly. First, I'd like to talk about the multidimensional generalization. So for the multidimensional generalization, this is a theorem by Daniel Behrendt from 1983. So we first have this torus. And now earlier we talked about multiplying numbers on the unit circle on the unit torus basically by by numbers here. But then the question is, I don't know how to multiply a vector by a number. So instead of talking about numbers in Z, then we look at matrices over Z of the same dimension. And we want them to be a commutative semigroup, because what we had earlier, because numbers commute, so this would be logical that here this would also commute. And the action would be the natural one. That is A times X is going to just be this action of a matrix multiplying a vector. So we say that this set is ID, that is, every orbit is either finite or dense if and only if the following conditions are satisfied. The first condition is that we have a pair of matrices that are rationally independent. So this is just like in Furstenberg's theorem, but turns out that this isn't enough. We need some more conditions. In addition, we also require that there must be some matrix in here that has a characteristic polynomial, that all of its powers, that all the characteristic polynomials of all the powers are going to be irreducible over Z for every one of these n. And then we have a third condition, And you could think about this in a different way. So for the third condition, we require that if V is an eigenvalue of every one of these sigmas, that is the following, that for every sigma in sigma, we have that we have some lambda such that sigma V equals lambda V. So if all of this happens, then there has to be some matrix sigma such that the lambda corresponding to sigma is going to be greater than 1 in absolute value. Well, when you look at it over C. So this basically says in a way that it doesn't, that these guys, they don't, in every direction, that's a common direction for all of them, that there must be at least one that expands that direction. That's a way of thinking of it. So
Noy?
let's talk.
Noy?
Yes.
Can you please remind briefly what is ID? What is this?
ID just means, ID just means that the property that every orbit is either finite or dense.
I see. This rigidity. Okay, thanks.
So let's talk about why these conditions are necessary. So I won't talk about condition 3. I'd like to talk about why condition 2 is necessary. So why must the characteristic polynomial of some sigma have this property that that the characteristic polynomial of sigma to the n must be irreducible for every n? So let's give a counterexample. Let's take sigma to be generated by these two matrices. These are clearly multiplicatively independent because a to the m is going to be equal to 2 to the m, 1, and b to the m is equal to 1, let's say b to the n, 2 to the n, and these two can never ever be equal to each other clearly. So they satisfy condition 1. Now, now I claim that you can find an infinite invariant subset for these guys that is not going to be dense. So the subset that I'm going to take is going to be the set of vectors where each coordinate contains either even or odd powers. For example, a vector that would satisfy this would be the vector in binary expansion, would be the vector, for example, 2 to the minus 1 and 2 to the minus 4 satisfies this because this guy, is there a question?
Yes, you can continue the explanation, but.
Oh, okay. So this guy here would satisfy this because this guy only has odd powers and this guy only has even powers. So this would satisfy this here. And now so that's an example. And I claim that because if you multiply by A, then you'd get something that only has odd powers from even powers. And by B, it's the same thing. It's basically built on the example that we showed earlier. So now I'll erase this. And in the meantime, Raz, you can ask.
When you say that sigma is generated by these two elements, you mean generated as a semigroup? Or
yes.
Can you explain a bit what is a semigroup or what we acquire there?
Yes, exactly. So this is just going to be the set of a to the m times b to the n, such that m and n are natural numbers. And in my sense, natural numbers means that they're greater than 1. So it's multiplicative, but it is not closed under inverses.
Okay, thank you.
So now we claim that this set here of those vectors that contain that each coordinate has only odd powers or only even powers is going to be invariant under this semigroup. And this is something that just builds on the example that we saw earlier. So this is why this condition is necessary. Those of you who are very ambitious can think about why condition 3 that is necessary. That's a condition that in every direction that's a common eigendirection for all of these matrices, must be one matrix that expands that direction. Think about why that's a necessary condition by building a counterexample. So earlier, so maybe this is a good place for any more questions. Does anyone have questions so far?
Can I ask something?
Yes, please. You can always ask.
So what about the sort of the axes?
Yes.
So one of the coordinates is 0. That's also invariant, no?
Where one of the coordinates is 0, you're saying something like a set like this. A set where either V1, V2, such that VI equals 0, exists I such that VI equals 0. Not necessarily, because it may not be invariant. Yeah, I guess, yeah, that's also invariant. Yeah, it is. Yeah, it's invariant. I'm sure that there's many examples of invariant sets here, and I just brought one. But I'm sure that there's many other examples, and in general, you could, but the reason why I like this example in a way, I guess that your example could work for many other sets, but the reason why I like this example in a way is because it also, if you switch 2 out with some other number, then you can just switch this out with, instead of binary expansion with respect to base n, and then you could get something nice as well. So, and clearly that set would not be infinite, so that's why this would be a counterexample here. So now, remember earlier that we talked about the generalizations, and we also talked about the positive characteristic analogs, and what does this even mean at all? So so let's first talk about the positive characteristic analogs now that we got here. To do that, first we have to explain what exactly happens in positive characteristics. So I'll do a quick review of what's called here, I think, field theory, field and ring theory. So of this. So firstly, in field and ring theory, this is the setting, and maybe your lecturers don't say it, but this is the setting. In characteristic 0, we start with a discrete ring. The discrete ring, which everyone likes in characteristic 0, is going to be Z. And now we take the field of fractions over Z. That is all of the numbers that are of the form A divided by B, where A and B are taken in Z. And what would that be? That would clearly be Q. And now in Q and in Z, we have a metric. With respect to the metric is just going to be the normal absolute value that we all know. With respect to this metric, you could take a topological closure. That is, what are all the numbers that their limit points of series in Q, and that would be R. And then from here, this is a bonus. We don't need it for our setting, but I'll just put it in so that you guys can enjoy more courses in algebra. So from here, for R, we can take the algebraic closure, and that's going to be C. And now the torus, as you all remembered, was R mod Z. That's going to be the topological closure modulo the discrete ring. So we can do this exact same thing in anything if we start with a different discrete ring. So the discrete ring in characteristic P, we'll take the discrete ring, which is going to be the ring of polynomials with coefficients in Fp, and we write that as Fpx. Then the field of fractions would just be the rational functions with coefficients in the finite field Fp. And we write that as Fpx, but not with brackets, rather with parentheses. And then the topological closures. So to talk about the topological closure, we need a metric here. So the metric here would be if we take some function f in, let's say, Fpx. Then let's start with this. F and Fpx, this is going to be a polynomial. Then we would want its norm here to be equal to p to the power of the degree. And then if we take a quotient, p divided by q, then this norm would be p to the power of the degree of p minus the degree of q. So this is just going to be a different, so this induces a metric on the space, clearly. And then after that, the topological closure is going to be with respect to this metric. And this is going to be the topological closure. We'll discuss this more further, and it's going to be the set of Laurent series that have finitely many positive powers and infinitely many negative powers. Not necessarily infinitely many, but it can be infinitely many. And here we have an algebraic closure, which I will not discuss. Those of you who are interested, I can give a name of an article later, which discusses this algebraic closure. And then here, the torus is just going to be as we thought, which is the topological closure modulo the discrete ring. That's going to be this. We'll discuss in the next slide exactly what all of these things mean. So going back to the setting and going in more in depth, we're going to take some prime p, and these guys here are going to be the field of Laurent polynomials that are going to be of this form here, where n is some number in z, so that means it has to be finite, and we can have infinitely many negative powers. And then after that, if we mod this out by the polynomials, that means that two of these functions are equal. If their difference is a polynomial, then we could take this following set of representatives of all of these series that only have negative powers. This would be our torus. So now we'd like to ask, what happens in this setting? Does Furstenberg's theorem succeed? What does that even mean? So what that means is, if we remembered earlier, in Furstenberg's theorem, we took two numbers and we wanted to look at what were the sets that were invariant under the times n and the times m. Where were n and m taken? They were taken to be numbers in z, which is the discrete ring. So here we would like to take two polynomials from the discrete ring, which is going to be the ring of polynomials. That's fpx. Is there a question?
Noy?
Yes? Yes?
Me? I'm confused. How do you get from the infinite series in negative powers to, how do you see this is a set of representatives? Oh, minus n. Okay, minus n. I missed the minus n. Sorry, I get it.
Oh, it's okay.
Yeah.
Okay, so now we'd like to take two polynomials from the discrete ring and look at what are all the sets that are invariant under both of these, under multiplication by both these polynomials. And we'd also require that the polynomials be rationally independent. And we'd like to see, if I have all these conditions, two polynomials that are rationally independent, then can I say that any set that's going to be closed, infinite, and infinite is going to be dense if it's invariant under these. And turns out that the very surprising answer is no. So Furstenberg's theorem fails in positive characteristic, and I'd like to show a counterexample. This is building upon a counterexample that Daniel Behrendt showed in a later paper in 1989. He showed something general, and I'm just going to show something nice, which shows why it fails in positive characteristic, and we don't have this in zero characteristic. So here, let's start with p equals 2, but we can generalize this for any p. And let's take f to be the polynomial x and g to be the polynomial x plus 1. So clearly, these are rationally independent, because if x to the n equals x plus 1 to the m, then we have to get that n must be equal to m. But then we can open everything up and we can find that there's going to be a problem, because in the end we'll still have, because even if we open everything up and let's say everything in the middle will be 0, we'd still have x to the n is equal to x to the n, let's say, plus all sorts of stuff, and then plus 1. So all of this thing here would have to be equal to 0, but that would be impossible because we have this 1 here. So clearly these polynomials are going to be rationally independent. But I'm going to construct for you an infinite set that's closed and invariant under product by both these multiplications. So let's start with the set that we like. We're going to start with all the set with this set here that only has even powers, no odd powers. What happens when you multiply it by x? If you multiply it by x, then you get the set that only has odd powers and no even powers. Okay, so this was the times 2 invariant set, which here corresponds to a times x invariant set if you take the union of this set and this set. Now let's see what happens when we multiply by g. So now I'm going to claim that g of x times p is going to be the set of sequences that have two coordinates are equal. And why is that? That's because if you take x plus 1 times, let's take some sequence n equals 1 to infinity of an times x to the minus 2n, and then we get on the one hand this sum an times x to the minus 2n minus 1 plus, so this maybe should be minus, sum an x to the minus 2n. So that says that we have a2n, which is this guy here, would be equal to a2n minus 1. So that's this set here. And now let's see what happens to this set if I multiply it again by g. So for this set, I'll multiply it again by g. So this is very simple algebra. I'll get this. But now remember, we're in characteristic 2. What does that mean? That means that this guy here is just going to die. It's going to be 0. And then this here only has even powers. So this is going to be, again, part of B. And then from here, we get, and in a similar manner, we could get that g of x times f of x is going to be the same thing, but I think here it's going to be plus 1. It doesn't really, and you can do the calculations yourself, but in short, you would get that g squared of xb is equal to b, and g squared f of xb is also going to be equal to b. So now let's take this set A, which is going to be b union f of xb union g of xb union f of x g of xb. I claim that this is going to be invariant, and that's pretty easy. Multiply under f and g, multiply this by f, you get here. Multiply it by g, you get here. Multiply this by g, you get here. Multiply this by g. When we multiply the set in here by g, we'd get here. And you'd multiply this by g, you'd get here. You could just do all of these. You take some element here, and then you'd see where it would go under all the products. So this is clearly infinite, invariant, and it's also closed because all the sets that we took are closed. So it's a union of finitely many closed sets and therefore closed, but it's clearly not all of the torus because if you look at this guy here, this is not going to be part of A for a few reasons. Firstly, it has both even and odd coordinates, so it's not in here and it's not in here. And secondly, it has consecutive coordinates that are not equal. Like for example, maybe 2, 3 are equal, but then if 2, 3 are equal, in order for it to be in here, it would need that 4, 5 would be equal, and they are not, so it's not in here. And similarly, 3 and 4 are not equal, so it's not in here. And now, so therefore, this is going to be a counterexample. Now, one can ask if why did it work here, and why would it fail if I took this exact same example and I tried it in zero characteristic? So the very simple answer comes back here. In zero characteristic, this guy here would not be 0, and it would just be like shifting. If instead of switching this x out, you'd switch all the x's out with 2, and you'd say this in binary expansion, then this guy here would be like shifting, and then you wouldn't, and then by doing this, you'd add more complexity, and you wouldn't go back to a set that you know, like B here, as we did here. So that's why this example doesn't work in zero characteristic, and this is a nice reason why things in this case work very well in positive characteristic, because if you add a number to itself enough times, then it will be 0 because of the positive characteristic. So now that we saw that this failed, then we can ask a natural question, which is what, in general, in mathematics, if we see that something fails in a certain setting, but it succeeded in another setting, then we can ask a very natural question of what conditions do I need so that it will succeed in our setting? So the question more accurately is, can we strengthen the condition in Furstenberg's theorem so that the conclusion can be true in this positive characteristic setting? That is, what's the correct notion of large? And by that I mean that if we noticed in Furstenberg's original theorem, then we said a set would have this ID property if it is not cyclic. So non-cyclic sets, non-cyclic semigroups are going to be large. And then after that, in Invariant theorem, we had that it would have all these properties, and it would also have some more properties. So in general, we could say that sets that semigroups are ID are, in some sense of the word, large. So the question is, what is the correct notion of large? Could it be infinite? Could it be, maybe I just have to take 3 polynomials and then I would succeed? I don't know. I wish I knew, because that would help me a lot in life. And a natural question to ask after this would be, what's an analog of Behrens' multidimensional theorem that would work in positive characteristic, or does one exist? And this is a question that, again, I have been trying to handle for the past month or so, I'd say, in my PhD research, since it could help me a lot with what I'm doing right now. And in general, are all those conditions in Behrens' theorem sufficient, or would we have to add more conditions? So that's another question when it comes to these two, when it comes to analogs. And now there's another question that we can ask. So notice that so far, so here I wrote measures. So far, we talked about the property of orbits are either finite or dense. Being finite or dense is a topological property. Oftentimes in dynamics, then people like to ask about topological properties, like are all orbits finite? Are all orbits dense? Can we say that they act like this or like that? Can we build closed sets that are infinite and invariant? And then after that, there is measure properties. That is, which measures are going to be invariant under this, and what do those measures satisfy? That is, can we have a same rigidity type result as we had in the topological rigidity of saying that all orbits have either this behavior or that behavior? Could we say something about measure rigidity, like all measures must have this behavior or that behavior? So here there have been many advances. There's been many theorems in this case that mostly talk about entropy as well, and that's beyond the scope of this talk, but I will have some papers linked in some of the bonus slides which regards this. And then there's another question, which is, we talked about commutative semigroups or abelian semigroups. What happens if we take non-abelian semigroups? Will the results change? Obviously, when you take it in one dimension, it's not very relevant since numbers are always abelian. But what if you take it in dimension 2 and above? So here there have also been results, both in regards to measure rigidity and topological rigidity, that again, I will not get too much into them since they're beyond the scope of the talk, but they will be in the bonus slides if anybody is interested. And now now another question that we can ask beyond more theoretical questions is questions about applications. So are there any other applications of these theorems? We saw an application in number theory and Diophantine approximation. We can wonder, can we apply these to any other fields? So it turns out that the answer is yes. Behrens' theorem is oftentimes used in Diophantine approximation of vectors. That is, how well can you approximate a vector with numbers with vectors with coefficients that look in a certain way? So that's one way of doing that, and oftentimes this goes through homogeneous dynamics, and that is the correspondence between homogeneous dynamics and Diophantine approximation. And there's also the question of, can we find any other more surprising applications of these theorems? Or in general, this is a very natural question to ask in mathematics, and it would be very nice to know if there's anything else. So that's all I have for today. Are there any questions?
I have a sort of general question.
Yes, what's your question?
So one of the first examples that you gave, right, it was this orbit nx mod 1, where
yes.
x is irrational.
Yes.
So you said that you gave this quick argument, since this orbit is infinite, it has to be dense, right?
Yes, yes.
But we know it behaves much more nicely even than just dense. We know that it is, uniformly distributed.
Yes, that's true indeed.
It's sort of I think a rather well-known application of Fourier analysis. Maybe this is how I know it. So my question is, are there generalization of this idea, maybe the ID property, but not only to density, but to some sort of uniform density or uniform distribution?
That would actually be very interesting. I'm not sure if there's exactly this property. Oftentimes the uniform distribution in order to have a distribution, you oftentimes talk about measure, and that oftentimes goes through the measure world and not the topological world. So for that, you oftentimes would use series which refer to ergodicity, for example, of these transformations. But then again, distribution requires measure, at least from how I know it.
Yeah. So in the positive characteristic world,
yes,
I'm not really familiar with it. So you don't have, you have a topology, so maybe you can have.
Yes, I think that you. So in the positive characteristic world, it would be quite interesting to look into it. You're not the only one who doesn't really know it. No, but not very many people know it very well. I'm sure that there are some basic theorems. There are some basic Diophantine approximation theorems. So I think that that there are some things regarding distribution there, but I don't know exactly what. But that's a good question.
Yeah, thank you.
Are there any more questions?
Okay. So if there aren't any more questions, then let's thank our speaker, and everybody is welcome to stay and chat. And if you have questions, think of questions while you're clapping. Then thank you for coming, and stay for a chat.
And stay for the list of